a great pleasure to introduce Alexander Itz, and he will be talking about a topic that is kind of, I feel, particularly close to my heart, so please go ahead.
Thank you. So first of all, I have to apologize for that I didn't realize that it would be so small. I still kind of, from the old world, I still like to write on the blackboard, and I don't know exactly what is the best way to arrange slides. So I decided this time to do this. I thought it is so, but when I do them, they look nice. but this, again, I apologize for having not thought about that it might be not very advantageous. Secondly, of course, I want to ask organizers for great honor to invite me. It is indeed an honor. I am kind of I do not belong to you guys, so it is really very honorable for me to be invited to some kind of indications that you know about me. Yes, and also it is, of course, the most importantly, it is a great opportunity. What should I put?
Mentorship.
It is a great opportunity for me to present what we are doing in the field of integrable systems. So I am myself. So when I am asking what you are doing, I am saying I am doing integrable system, which is difficult to define, and there is a very good definition which belongs to either to Henry Makin, or to Hermann Flaschka. So when he was, some of them it is not clear in the history, was asked what does it mean integrable system, the answer was you don't think I can solve it, but I can. So this is indeed some very good definition. But in the serious way, the main analytical tool in the theory of integrable system is the Riemann-Gilbert method. So it is with a different flavor. It is not just like what you say in diffraction, but there is one interesting intersection. So the part of our Riemann-Gilbert approach, it is a so-called algebraic geometric integration, which started in the mid-70s from rather famous works of Novikov, Sergei Petrovich Novikov, then also Marchenko, and some other people. And it is indeed, can be then, at some point, we realized, much longer, it was somewhere in the zeros, that it can be indeed transformed to the issue of factorization matrices, which are algebraic, whose entries are algebraic functions, elementary algebraic functions. So, and this is I decided to present it. So the message is, I want to present the idea that every algebraically depending matrix function can be factorized using theta functions, Riemann theta functions. And I am going to do it in the example. It will be case study, as it is said. It is going to be this is going to be case study. So I will take the matrix to factorize from this question. I will later on. I will kind of so I will talk in reserved way. So first I will talk about factorization on one concrete example, but then I will explain what its physical meaning and so why it is important. So this example is simple, but still it really it has some extra bonuses which simplifies the task, but it has all the necessary features. So this is a work which been done long ago, in fact, in the 2004, 2005. So this is was done. We started it with Karepin and Jin, Takhtajan, then more general was considered in my work with Mizadri and more. And what I still expect that it should be, what we are doing should be strongly connected to the works in diffraction by Yuri Antipov, Sylvester Zemlyanin, and also, as I was told just yesterday, by Amera. So she is talking after me. So it is interesting too. So we're still discussing with Euro. We're still discussing our kind of intersections. So I believe that this is where we are. Problem. So I will just start with the problem. So I want to factorize. I want to given consider this matrix. Well, it is given on the unit circle, but the function, so lambda is a complex parameter, not equals plus minus, or just a parameter of the problem. And phi of z, it gives dependence on z. So it is a square root of this ratio when p is a polynomial of zg, and all zg and zg minus 1, they are all different. So this is the problem. So I want to, well, this is something which is probably I will skip because it is a convention how we enumerate all those z's. So I introduce the set of lambdas which coincide with this as a sets, and then there is some So this is if I will later on consider simplified situation when all my lambdas, all z's are real. So it means that I just have line of increasing real lambdas. But if it is not, again, in the physical problems, there might be complex as well. So everything depends on the physical parameters. Magnetic field, anisotropy, so and this is important to have these different pictures and to be able to handle this differently. But we will do it, as I said, in the simplest way. I will assume that all those lambdas are kind of, like this. So this is the description of the function which I want to factor. And the question is kind of, find UP, U minus, analytical inside, analytical outside, normalized by identity, and represented. So Wiener-Hopf factorization. This I want to find U plus, U minus. Okay, first step, very natural, everybody does it. So Yuri also does it, of course. So what I do, I just diagonalize matrix phi on the, so this is a diagonalization. This is the eigenvalues of this matrix, my parameter lambda is involved. And this is just, elementary what matrix is eigenfunction which diagonalize this matrix. There is a bonus of this problem that this diagonal part is constant. This is a kind of extra bonus, but it is not necessary to proceed. So, as I said, I am now assume that all lambdas are real, and I introduce the set, which is kind of which is a union of intervals: lambda 1, lambda 2, lambda 3, lambda 4, and so on. And I would assume that all lambdas until 2n, they are inside unit circle. All lambda greater than for j equals to n plus 1 and beyond, they are greater than 1. Okay, so this is, and what is the main observation? The first observation is that, of course, my function q, it is this one function q, this one. It satisfies a certain Riemann-Hilbert problem on this collection of these intervals. So if I consider function q coming from here and there, it is continuous. So my square root is defined exactly on this set of, I forgot to say that. But if I go on the intervals from up and down, then of course I just interchange the columns. So phi z changes sign. So it means that that kind of the first observation is that my q satisfies, q is analytic outside of this collection of intervals. On the intervals it has jump given just by sigma 1. While on the edges it has some special singularities which can be explicitly, of course, characterized. So this is when Zj with plasm, it is just square root, it is 1 over square root. So this is just from the explicit formula of Q. This explicit formula of phi, we have exactly this thing. And at infinity, I have just, this constant matrix. Okay, so Q is, so this is those Q chi are invertible. So this is a collection which, by the way, determines, of course, function Q uniquely. So that is just very simple Riemann problem which is solved by my Q, my eigenvectors. Next, step 2, also natural. So now so I want to factorize matrix phi equals u plus u minus. Now matrix phi is given like that, yes? So I move q lambda minus 1 to the left, u plus to the right. So I have this function equals that function. So if I introduce function s, which is outside of the unit circle, it is this part. Inside of the unit circle, it is this. Then, of course, what I would have that this function s, so it is defined on the unit circle, but of course it is continuous to everywhere, and it also can be characterized as a solution of the following Riemann-Hilbert problem. So, it is, you see, it is of course again analytic outside of my cuts. It is the same sigma 1 while until lambda to n when I am inside of the unit circle. You see, inside of the unit circle, the jumps are given by q. U is analytic function inside of the unit circle. So jumps are the same as q. So for all lambda which are inside for all intervals which are inside unit circle, I have the same jump as q. But outside, of course, I have to conjugate this q with this diagonal matrix. So what we have that's what I just said. So inside I have the old jumps. Now I have kind of twisted sigma 1 by this lambdas. Twisted sigma 1 by this lambdas. And singularity at the edge point more or less the same. So again, inside it is exactly the same matrix, right matrix as for Q. Outside it is just conjugated with this lambda. And there is something at infinity which I cannot say, it is not visible. Very well. So again, I want to emphasize what has happened. So when I am, make this diagonalization of my original matrix phi, first I get this Q, which is this Riemann-Hilbert problem. Now I go for S. It means that I just twist those guys. So now the problem is to find S. So now this is the the problem is to find S. And this is where we need algebraic geometry. This is where we need to go to Riemann surfaces. So I just have to present the solution. I'm going to solve it for you. To present the solution, I have to introduce certain ingredients. So main ingredient is this hyperelliptic Riemann surface. It is two-sheeted, realized as a two-sheeted, exactly my intervals. It is the intervals when I grew the two sheets. And my original, and so I believe that the upper sheet, it is characterized by y to be positive over there, and the lower sheet, it is negative. There are two infinities, infinity plus minus, plus infinity plus. It is on the upper sheet. It is when it is z goes to infinity, y behaves as plus z to the n. And infinity minus z goes to infinity, y behaves as a minus z to the n. And in my original plane, when I set my Riemann-Hilbert problem, I now identify with the upper sheet of my. So from this point of view, from the point of view of this Riemann-Hilbert, of this hyperelliptic curve, Riemann surface, my Riemann-Hilbert problem is set on the upper sheet. And so this is, it is easy, of course, to calculate genus. It is the genus is 2n minus 1. And what next? So we have Riemann surface. Then we have next it is to introduce the basis of holomorphic differential, the abelian differential of the first type. So genus 2n minus 1. So I have 2n minus 1 holomorphic differentials. So this is a holomorphic differential. They are holomorphic everywhere on the Riemann surface. For those who not very familiar with this, the point is that of course I have square root singularities here, but those square root, it is in fact differential of square root upstairs. And square root, say, z minus lambda j, it is exactly the local coordinate on the Riemann surface near the branch point. So this is a holomorphic. And the power of z is exactly such that it is integrable singularity at infinity. So it is. So this is there are exactly 2n minus 1. The usual normalization. So those c uniquely defined by this n 2n minus 1 condition. So I want all so-called a periods equals 1. Now, what is this a? This is yet another important topological ingredient for the Riemann surface. So A and B's, as they presented here, it is the basis of the first homology group of this Riemann surface. So all A, it is I go around on the upper sheet over my intervals, and B, say one, I started on the upper sheet, then I go to the lower sheet, and I'm back. So this is the standard choice, one of the standard choices of A-B cycles. And I also want to emphasize that those guys are quite simple thing. Of course, integral along every A, it is just the double integral between those endpoints. And in this formula, I want also to emphasize that when I'm talking about Riemann surface, then I use letter, what it is, zeta. When I use letter zeta. When I am on the upper sheet, it is becomes z. It becomes z. So here it is, so this is it means that I am on the upper sheet. Okay, so this is a holomorphic basis. Holomorphic basis also, with holomorphic basis, the very important thing is associated. It is a B matrix of this Riemann surface. So now my A periods are normalized, and I can introduce B periods. And by the way, they're also very simple. It is just the sum of it is the sum. So B periods is going to be the sums over those guys. In between. What is important? B is, it is again general fact from the theory of Riemann surfaces, that B is symmetric matrix. Its imaginary part, it's not imaginary, but it is positive definite. So imaginary part of B is positively definite. And now theta functions. And there are very important typo here. There should be pi I. I am sorry, so this is a kind of multiple Fourier series. So this is a Fourier, guys, and then it is the weight, so to say. And of course, I unfortunately forgot to put pi I. Because exactly having this pi I and having this condition, I would get a wonderful convergence of this series. Those brackets are defined as a kind of scalar product, but it is a kind of real, it is bilinear form. It is not without any complex conjugation. So it is just this. And fundamental properties of theta function is that it is, first of all, it is of course even. And secondly, if I add n plus bm, it is a, well, I can use the language of lattices. So if I add, but I don't want to use it, although it is essential for some non-trivial applications. So if I add this combination, n is integer vector and m is integer vectors, then n is not filled. So if I add n, it does not matter, it does not change. But this part is filled. So it is just I get theta x with this factor. This is very important. With this factor. Okay. So this is a theta function, which as a function looking as a function on c to n minus 1. But now I want to use this theta function to construct function on the Riemann surface. To this end, I introduce a vector of abelian integrals of the first of my omegas. And I introduce a function which is the function which is already defined on the Riemann surface. Well, it is of course not single-valued function because of the previous, but I want to look at this not single-valuedness in a more detailed way. In fact, I am going to, okay, I consider this object, well, C is just arbitrary, consider this object as a function on the, I take upper sheet, take C, and cut it over the R. Then I can, of course, define this object as a single-valued but not continuous. So, how I do it? I decided that I would integrate my abelian integrals if z is in the from lambda 1. If z is in the upper plane, then I go just any curve which totally lies in the upper plane. This way, this way. If z is in the lower plane, then I go this way. So everything is unique. Everything is defined as one-to-one, as single-valued objects. Now, important is how those omegas behaves when I begin to approach real line. So when I approach a real line, so when I am here, then nothing changes. So this is just there is no, it is just inside. But when I am there, then the difference, then the sum is 0. When I am there, then the difference of omega plus omega minus is exactly this integral. And this integral is actually this integral, so it is a period. When I am this, when I am over there, okay, this is a period. When I am coming from this top and sum them, sum omega plus omega minus, then this part cancels, and what this cancels, what I have integral over there, so b1, and so on. So this is what I want to say. So I want to say that that difference of omega g plus omega g minus on those parts is 0, but in any dots, in any interval which between my main intervals, then it is just 1. Then it is the sum of the A periods. When I am on the interval, then I am talking about the sums of omega. So omega g plus omega g minus, it is 0 on the first interval because it is just integral from here and plus integral from there. They just cancel each other. But when I am, as I said, when I am somewhere here, then I am going this and I get exactly the sum of the integrals over these dotted intervals, which is b. So the sum of omegas over this, it is bjk. So that is very simple, very kind of, there is nothing. You don't need to know anything. Now, yeah. So as a result, what we have for theta function? So the combination of this thing and the combination of this leads immediately to the following behavior of my theta function. So for any c, I would have theta functions on these parts. They just don't change. And they don't change in any of this part, because then it would just add integer. And adding integer is illegal. It is innocent operation. So when I go, but on the other hand, when I am go to my bold intervals, then in the first one it is you remember omega plus omega minus equals 0. So omega plus equals minus omega minus. And because of the evenness, I can rewrite it as omega minus minus c. So for any other bold interval, of course I have this, but also there is an addition of b, and so I would have this factor going out. So this is the jump properties of theta function. We're almost ready. We're almost done. One more ingredient. There is of course two more things. Fundamental fact, which is this is in this particular case for hyperelliptic for this case it can be actually proven, even without referring to general facts of the theory of theta functions. But nevertheless, there is the following general fact, which I apply to my hyperelliptic curve. If I consider if I consider point zeta j, 2n minus 1 of those points, and such that their projections on z plane don't coincide, different. On the language of Riemann surfaces, it means that the formal sum of zj form a non-special divisor. Then the following is true. If I consider my c take in this particular form, so this is the sum of omega of over zj minus some particular half period, I skip explaining, and not can be explained in a simple way. It depends on how we choose canonical basis of first homology group. For this particular case, I forgot it. But it is not a very big deal to recover. So it is some concrete thing. And then the statement, the kind of Riemann theorem, is this: that first of all, as I said, it is not identically 0, and secondly, it has exactly m minus 1 zeros at this point, at the given point. And in particular, if I take those zeta j as my zj minus 1, then it's going to be zeros exactly at this branching points, and no more. So this is why. So now everybody can kind of appreciate the importance of this object. So this is just the product. So when we are on the Riemann surface, on the plane, how we can organize functions which has given zeros? We consider products. Z minus z1, z minus z2. So this one, it is the analog of this product for high genuses. So that it is a block. It is a building block in the theory of functions. So using these functions, you can now build meromorphic functions on the Riemann surfaces. Okay, but go back to our. We have one more ingredient. One more ingredient, and I am going to write the answer. One more ingredient. So it is a so-called integral of the third kind. So I consider again. So I consider on my Riemann surfaces. So this is, you see, when it was when there were no this term, it would be the integral of the first kind. It would be holomorphic. Now I add z to the 2n minus 1, and so it's at infinity. It behaves as 1 over z. So it is not integrable at infinity. It behaves as a logarithm. This is by the terminology of Riemann surfaces. It is an abelian integral of the third kind, which has, and I normalize it. I normalize it in a little bit tricky way, not in the usual way. usually those integrals normalize to have all a periods 0. I don't. I have only n minus 2 periods 0, but the last, over the last circle, it is pi I. Anyway, it is easy. So it is again linear system, solvable linear system for my C. I can determine it. And then again, I can also notice it that there is this. So first of all, at infinities, it behaves as plus minus 1/2 logarithm Z. And it looks similar to, its jump condition is similar to my omega. So on these parts, it is delta plus equals delta minus. In any other parts, dot part, it is pi I. On the parts which are bold, it is again on the first one it is 0 and then plus, and then it is b period of this. Okay, now we are ready to present the answer. So now we are ready to present the answer. So, to S problem. So the S problem is given. Well, all this comes from the original kind of normalizations. So this is easy. This is elementary. Now this is the object which I going to construct, which I want to have my this sigma 1 and sigma 1 twisted jumps. Here it is. So each element, each matrix element of this matrix is a ratio of theta functions. And the argument, first of all, you see this argument are arranged in a way that, okay, that this thing has poles, that exactly the 2 minus in the needed. So this thing together with this one guarantee that I have needed behavior at endpoints. Jumps are follows from all the previous behaviors. So when I say when I have to add omega plus, when I am going through the bold things, then it means I have to add B. So when I add B matrix, I have exponential terms going out, everything cancel, except this kappa and this thing. And this kappa cancels B periods, the jumps of delta. So my point is that, and this I skip details, but we can just look at it. So that it is absolutely straightforward. You just kind of put on the left side all the my jump conditions, and you begin to see that when you jump, there is no jumps between my bold intervals, and on the bold intervals, this theta 1, 1, theta 2, 1 becomes theta 1, 2, theta 2, 2. And it becomes, if I am inside and if I am outside, you see, I forgot to say this E. This E, it is a vector which has all 0 components for kind of corresponding to my intervals inside unit circle. So there is no this term. I have just sigma 1 matrix. And outside, it appears outside, it is exactly responsible for this twist. It exactly would be responsible for this twist. So once again, this is up to the routine checking, of everything. This is a solution. So this is a solution. And now I'm going to, so when, it is especially simple, although not everybody would agree, when n equals 1, it is elliptic functions, of course. It is elliptic functions. So it is a factorization. This is why I reacted on Dayton when he said that when matrix is factorized by elliptic function, it is not factorized. To me, it is. It is the answer. So now I have what? I don't have.
You have it.
Huh?
9, right? 9 minutes.
I look at 9. Oh,
Yeah, you have 9 minutes more.
it is shows
Until
how.
podcast.
It is shows how. Okay, good. Very good. So now very quickly. So what? How we go to entanglement? So application to first of all application to Toepler's determinant. So this is the Toepler's determinant. So this is the usual definition of Toepler's determinant. It's the usual question. Calculate L by L determinant. Calculate its asymptotic as lambda goes to infinity. This is the classical objects, Seguin theorems, Widums, and everything. But of course, the interesting thing is that my phi is matrix now. So my phi is matrix. And there is a nice formula by Widom that if I differentiate, well, it is more general, but I apply it to my case. So if I differentiate in my case, differentiate this logarithm of Toepler's determinant by lambda, first I get linear term by lambda, and this is just average. It is just the average of the logarithm of determinant. And then I will have 1 over 2 pi, and this is a constant term. It is a trace of these differences of, well, V plus it is the inverse factorization. In this case, it can be just calculated using U. But in principle, it can be done independently, of course. So it is very interesting. It is a paper, there is a known, classical paper of Harold Widom, when he derived kind of analog of Seguin theorem for block Toepler's determinants. And in fact, it is very important theoretically, but it is not very useful practically, because he gives the answer in terms of, again, infinite determinant. So you just take, so this part, of course, present, but then for the constant, you have to take the limit Toepler's infinite matrix. Take t minus 1 sigma, and then take determinant. So it is practically this is really difficult. But in his paper, there was, we call it now intermediate Widom theorem, which is given by this formula. As a matter of fact, we derived this formula by ourselves, using, by the way, another part of the Riemann-Gilbert method in integrable systems. And it was very interesting. I wrote a letter to Bazor, to Widom, showing this formula. That's what he said. And only in a year, when Widom came to our department, gave talk, I again showed it to him. And he really, look, let's go to the library. It is not surprising why he kind of forgot about it, because in his derivation it played intermediate role, because he kind of thinks that factorization, that if you leave the answer in terms of UP, U minus, it is not very efficient. It is kind of, you introduce transcendental element in the answer, kind of. But the point is that we can write it. So as a matter of, so we can do it, and so this is answer which we can obtain from our formulas. So this is, of course, this is a determinant, and this is a ratio, this is a product of those theta functions. Very simple described. So this is the answer, this is a kind of Widom constant, which is for this particular phi. So for n equals 1, we derived with Jin and Karepin, then we derive it for general n with Francesca Misadri and more. Also, as I said, all this kind of flowing in integrable system. So Mattia Kafas, more or less simultaneously, considered more general block Toepler's determinant appearing in the Krichyver's theory of Capet equations. So that is where we have. Now, 4 more minutes. application to quantum entanglement. Now, what is a quantum entanglement? Well, this is, of course, a fascinating thing. So I would suppose I have the system of n spins. And I kind of select subsystem of L spins, neighboring spins. And then I want to push, first of all, n to infinity. And I want to see if this subsystem is entangled to the whole system of spins. So, which is, of course, so what does it mean? Exactly, it means the following. So if I am on the zero temperature, then there is density matrix. So every quantum system is characterized by so-called density matrix. It is a positively definite operator, ρ, such that if you want to calculate any vacuum of any observable operator, you have to multiply this operator by ρ and take trace. So this is a density matrix. So usually it is a kind of, this density matrix is a kind of a convex sum of pure projectors. But if t equals 0, then it is indeed my system in the pure state. It is a ground state. Well, I can split my Hilbert space according to this subsystem. Subsystem, part of the state corresponding to the L and part of the corresponding to n minus L. And then I can trace out everything which is outside of L. And I get so-called reduced, and I also put n to infinity. And I get so-called reduced density matrix. And now in the term of this reduced density matrix, we can formulate what does it mean exactly the subsystem is entangled or not entangled. If this rho L is again projector, then the system is unentangled. If it is not, but in general case, it is not projected, so you have to characterize this situation. It is a Bonnet, Bernstein, Popescu, Schumacher in 96 suggested as a characterization this Neumann entropy, trace of rho L times logarithm rho L. So if it is again projector, then rho has spectrum is 0 or 1. So this SL is 0. But if it is not, then if it is positive, then it means that it is not, it is entangled. So it means that this density matrix is not projected. So interesting to calculate. So the principal question is this. Now, connection to the Toeplitz determinant. As it was discovered by Jean Karepin using the previous works of Lataré, Ricci, and Vidal, the limit is given by some integral involving my Toeplitz determinant. And I know the formula for this Toeplitz determinant, and so I get S infinity as this explicit formula. And now for those who does not like elliptic functions, for n equals 1, I want to say that this is an absolutely ultimate answer. For n equals 1, it is XY system. We calculated this entropy exactly in terms of just complete elliptic integral. Who is H, who is gamma? It is the original physical data. So this is a Hamiltonian for the XY. Gamma is a coefficient of anisotropy. H is magnetic field. So this elliptic function formula yields absolutely ultimate formula for this physically important thing. And there is even more. We can calculate spectrum of this from that formulas of reduced density matrix. Spectrum multiplicities, and they are given in terms of some number theoretical combinatorial elements. So this is thank you very much. So minus.
Thank you. I have one question, but please ask it only if you suspect that the answer is short.
Okay. But when you factorize these matrices using this formulation of theta functions, are the factors commutative?
Huh?
So when you've done a factorization of a matrix, and a big question for Wiener-Hopf factorizations is often, are the matrix factors commutative? So if you multiply them in opposite orders.
No. This is the whole point. So my original matrix phi, it is not commutative for different z. No, it is. That's the whole point. So if it is commutative for z, this is the case when I can solve, when I can take logarithm and solve the system immediately in the integrals.
So this is a more general class of matrices.
No, yeah. This is thank you for your question. It gives me opportunity to emphasize that what we are doing genuine factorization of a genuine matrices. So this is what it is.
Okay, thank you very much, and I'm sure there are many more questions, but we have a coffee break coming soon, so there will be plenty of time to ask those questions. Thank you very much again.